Okay, back. Okay, before we really get to what we're talking about, you guys probably realize that we use a lot of Greek letters, right?
Yeah.
I want to say something about Greek letters. For instance, if there are three angles we want to deal with it, right? We call it alpha, beta, gamma, and then I think we use theta and phi, right? I hate. Well, anyway, all right. There is something about this. Alpha, beta, gamma, theta, phi. These are what we call English pronunciations. And actually, for all the I's, right? Greeks say phi. This is phi. This is theta. Okay. And this is what we say beta, right? What they're really saying vita. This is uh, this is gamma. They don't have in Greek there is no God. They say this is wama. Okay. Okay. Let's say you want to be pure about this, right? You say I want to do this as a phi. You want to do this as theta. Oh, actually, if you ask me, right, I prefer this to be pure. You call this a theta, call this phi, instead of theta and phi, right? Now this is the problem. How do you call this thing?
P.
Yeah, that is a problem. Okay, your teacher asked me, what's the circumference of this circle? You say it's to p. Okay, this could be a problem. Yeah, because this is everybody call it pi. It's so entrenched into the English language that you do have a problem with this. Okay, there are some other things I want to, since we're doing this, there's other things I want to point out. That is delta. We use delta as we use delta x to mark a segment of x, which is not infinitely small. Infinitely small, we call it dx, right?
Yeah.
A finite segment on x, we call it delta x. Delta, this is capital, small is this. Okay.
Yeah.
This is also called theta, but this is almost, I think, going along with pi. You call it delta. You don't go around and call this theta, because this is going to be a problem. Then there is this, there's really U and V. I mean, I'm sorry, this is M and N. This is called mu. This is called nu. Okay? In the, I don't know. This is me, this is ni, if you say it in Greek. I don't know if you're going to say mu or nu. You saw this is me and this is ni. It's probably going to be problems. So these pi, delta, mu, and nu, probably you don't want to change it. Theta and phi, probably you don't want, you say theta and phi, that's probably okay. This is all gets to be, there's a painter called Van Gogh. You go to Dutch people call them Van Gogh. This is pronounced in Dutch Van Gogh, by the way. I'm sure you go to Greece, they call this, I don't know, I've never taken a math class in Greece. I don't know if they call it P or pi or whatever. They probably call it P anyway. But since we're talking about this, there's a couple of things I want to point out. This is called a phi, right? There's another letter. It's looking like this. It's very similar to it. Okay.
Yeah.
This is normally used to do a angle. We use this to do an angle. Right? This is the phi sub 0.
Yeah.
We use this to denote a angle that's whatever. Okay, is psi is normally used to denote a function, especially a wave function or some other function. And then since we're doing the psi, which is also normal in English way is called psi, right?
Yeah.
Then there's this thing. This thing you've probably seen before. Have you seen this thing before?
No.
This is xi. This is psi. This is xi. Okay.
Okay.
And the way that when I learned this is all psi, psi, or whatever. And let me see. What else do I have? All right. Then there's the last one. Is this one? How do you call this?
Sigma.
Sigma. Yeah. And this is used to do what?
Sequences like like infinite.
Add them up, right?
Yeah.
Sequence. Add them up. You have a sequence of fnx or whatever. I'm just making this up. You have a sequence of n, right? You add them up, and from 1 to say 5, right?
Yeah.
This is 1 plus 3 plus 2 3
1 plus
1
2
2
plus
3 4
3
5.
plus-
Add them up together, right? Yeah. And also the lowercase is also sigma is also used. That's used as at least this is used as a deviation in the normal or Gauss distribution. You say 1 sigma. You know 1 sigma is 68% or something. They're within the error. That's Gauss distribution look like this. This is almost like any kind of distribution, right? Normally, like all of these in this range is called you're within 1 sigma. This is the sigma. This is 1 sigma. Yeah.
Yeah.
This is called within 1 sigma. Then within 2 sigma is probably 90%. I don't know, but within 1 sigma, that is 68%. Another sigma out. That is I don't know. I don't want to guess. There is a quality control thing. They call it 6 sigma. They extended out 6 sigma, and then the outliers are the bad products. Almost none. Okay. The guy who did this, they call Ed Deming. The Americans don't care about him that much, but in Japan, this guy is God. This is way back, way back when. Okay, last one I want to talk about. This. What do you call this? Iota. Iota. You ever heard of the word iota?
No.
When you tell me, like for instance, I can say it, right? Say, when you tell me you're not playing computer games,
Yeah.
I say there's not an iota of truth in it. Right? Not a little bit of truth in that statement. Right? It's not a iota of truth in it.
Okay.
Greek people don't call it iota. Okay, I think we got enough fun, right? Let's do some real physics. All right. When you have a force on an object, right? Let's say you put a force on this block, right? You put a force on it, right? This is okay. We just did this. We call it theta, right?
Yeah. You call it theta.
You call it theta. That's okay. Whatever you call it, it's okay. So this force you put it on this block, right?
Yeah.
Separate it into the parallel one and the vertical force, right? Let's say this thing start moving.
Okay.
And then you did work to this mass.
You did what?
Work. You did homework. You worked on it.
Okay.
You transfer energy into this piece.
Okay.
This is called work, right? It is really, let's say they moved in this way, right? This let's call it S, right? Move the distance S.
Yeah.
It's really F. S. What?
Huh?
It's this F. So it's F times cosine theta, right? We call this as a vector, right? Call this the vector.
Yeah.
It's moving. This is the way it's moving. This is the force on, right? Actually, for this kind of thing, we just say F dot S. Okay?
Okay.
Dot product. Okay? Oh yeah, we didn't really get to the unit of this, all right? Oh, for instance, the force, right? Force equals to m times acceleration. What's m's unit?
Grams.
Kilograms. So it's kilogram. The unit of force is kilogram. Then it's meter. Then it's second square. That makes sense?
Yeah.
Does it make sense to you? This is acceleration. This is distance. dt twice. Every time dt, you carry a second over. Yeah?
Yeah.
We call this, by the way, we call this Newton. Okay? And you ever heard of Newton? Okay.
Yeah.
Okay. This is a Newton multiplied by meter. Right? This is Newton multiplied by meter. Okay?
Yeah.
Let's say you keep doing this. Right?
Mm-hmm.
You keep doing this, there is a per time how much you're doing. If you keep doing this, right?
Yeah.
You do this. How do you do work? I just call it work. This is the work you did, right?
Uh-huh.
Okay. Per time, let's say the work you put on this thing in this period of time. Okay.
Yeah.
This unit is Newton meter divided by second. Right?
Okay.
Newton dot meter, Newton times meter is called joule. I hope I spell it right. Divided by time is called watt.
Uh-huh.
Okay, you ever heard of this?
Yeah.
Yeah, this you heard of, right? This is per time power, like electricity, right? You have this light bulb, right?
Yeah.
60 watts. That's how much. This is for every second. It takes 60 joules of energy to burn, which comes to, you can get to Newton meter, convert it to mechanical. You can convert it to how many, if you're gonna push a block and convert all that into electricity, and you can see how much we're talking about, right?
Mm-hmm.
Okay. Okay, let's just do some since we're dealing with the units, let's do some other units. 1 horsepower. 1 horsepower equals to 745.7 watts. Okay?
Yeah.
Can a person produce 1 horsepower of energy?
No.
Okay, let's say a person has 50 kilograms weight.
Yeah.
Yeah? And he's gonna jump. I think the world record is 2.45 meters, right? He can do that in half a second. Okay?
Okay.
This is, I'm going to just write this out, okay? The power is the work divided by time, right? So it's 50 kilogram, 9.8. This is gravity, mg. He's overcoming mg, right? Overcoming the gravity.
Yeah.
For 2.45 meters. Right? In half a second. Right?
Yeah.
This gets to be 2400 watt. This gets to be 3.22 horsepower. So if you do high jump, right, for that fraction of a second, you are actually producing a horsepower of energy.
What? Oh.
Oh yeah, normally no way you're gonna produce. If you say you pull a card, right, there's no way you're gonna do a horsepower. Horsepower is about what a horse can do. Yeah. This is the good old times when they just come up with this car, right? And they just say, what's the power of this car, right? This engine. Is it 3 horsepower, 4 horsepower? At that time, people use horse to pull cars. So they have very good idea what's 1 horsepower, right? How much 1 horse can do. And by the way, if you use 2 horses to pull the cart, it's not two horsepower. Because they're not both every horse doing a fraction of a horsepower. Just the nature of pulling. I think 3 horses don't produce 2 horsepower. You understand this? When 3 are pulling, there are times the rope is loose, and some other horses, there are horses that they can be lazy about this when 3 horses are pulling. 1 horse can just walk along and not pulling. You understand this? Yeah, that happens. Okay. Anyway, let's do one more thing. Let's say a person in an elevator, right?
Yeah.
This is the elevator, right? This is the person in it, right? Person in the elevator, right?
Yeah.
This elevator is moving. The elevator is moving. The person is not. Okay.
Yeah.
So the elevator obviously is doing work to the person, right? Is at a certain speed, constant speed, right?
Yeah.
But for the person inside the elevator, he's not moving.
Yeah.
Is he? So he's not moving, and then there's no power. No work done on him. So is there work done on him or not?
Isn't the elevator doing all the work?
Yeah. For us, right? We see this guy's moving up. Of course, it's doing work, right? The elevator put the force on him, and then he goes. But for him, he's sitting there. I don't know. Don't be doing any work. I mean, I'm just staying here, not moving. For him, he doesn't know it's moving or not. He's just inside the elevator. Say there's no window on the elevator. What's the problem here?
Gravity.
Okay, I'm not gonna say anything about this guy. This homework. No, please, no bad words here. Huh? Explain what's going on. Okay, now we do a force. Put a force on an object. Yeah, we put a force on an object. Yeah, and this object gonna move. Then put a force on an object. This force gonna transfer. Then this is gonna transfer into velocity. The work is gonna transfer to velocity. Let's say there's no friction or nothing.
Yeah.
All force is transferred to velocity. We want to see what is going on here. What's the for force, right? This is the force that goes along dx, right?
Yeah.
That's the distance. This is the work, right? And then I just take an integral of it. This is the work that's done on this piece of object. Let's say from velocity equal to 0 to velocity equal to v, right? A certain v. This is, we're not talking about, we just, we understand that. This is a variable, this is a fixed number. Right? So let's take a look at this, okay? What is it? F equals to m dv dt, right? That makes sense? This is the acceleration. M
Yeah. That makes sense.
dv dt equals to x. You do x twice, equals to do v once, right? Because once, v already did once.
Yeah.
Yeah. This is dx. Right?
Yeah.
Okay, I'm gonna write this slowly so you see it. I'm gonna transfer this dt from this side to that side. I'm gonna transfer this.
Yeah.
Makes sense, right? What's dx dt?
Dx dt, that's velocity.
Okay, yeah. Let's write this first. People go sit back and. Okay, now all of these x and v's and whatever dt's, right? You can freely move around. And you can freely move around because all they are moving according to dt. This dx is when the t changed that much, how much does x change?
Yeah.
This dv is when t changed that much, how much dv change? They all linked up together. So it's all the same thing anyway. So you can do this, right?
Yeah.
Okay, now I'm gonna keep going. I'm gonna write this. actually m just come out. M is a constant. The thing, the weight is not changing. What's this?
That's this. Wait, that's v cubed divided by 2.
V what?
V squared divided by 2.
Yeah. Okay. This is m v squared divided by 2. Okay. We're gonna write, right? This is from 0 to v. Okay. This is all 0 from 0 to v. Okay. I'm gonna write it a little bit different way. Okay. Okay. 0 is 0. V is v, right?
Yeah.
So it's this. This is if you do a certain amount of work. Okay. If this work all transferred to velocity,
Yeah.
this is we call this kinetic energy.
Okay.
I'm going to give you an example so this make more sense. Okay. Let's say you have a ball that drops. Okay. Drop a certain distance. Let's say h. Okay. This ball's weight is mg, right?
Yeah.
So the work mg did is mg times h.
Yeah.
Let's say this thing sucker is not moving here. We want to know this mg h. This is the work that's done from here to here, right? All this work is transferred to velocity. Okay?
Yeah.
So you get this. Right? So velocity equals to m cross 2gh, right?
Wait. Isn't there? Oh, okay, never mind.
Yeah. This is, by the way, I lost a page. Do I have that page? Yeah. Remember back when we did this?
Yeah.
The acceleration is, instead of a is g. So the velocity is 2gh. It's 2ax. We're talking about exactly the same thing here. Okay.
Wait. That's v squared should be.
Oh yeah, right. This is already.
Yeah, I got really
Yeah.
confused.
Okay.
Yeah.
Let's do an example on this. Just sort of get you into this. Let's do a wedge. Okay, so the wedge. This is theta. Okay.
Yeah.
So you have this F, which is mg, that goes to F parallel and F vertical. Right? So this is F, this is mg, F is mg,
Yeah.
this is mg, this is sine theta. Okay? This is theta, by the way. If this is theta, this is theta. Okay?
Yeah.
This is mg cosine theta. Okay? Yep. From that, you can do all your business. Okay? Now, let's get it a little more interesting. Let's say you have a thing like this. Okay?
Yeah.
This is a circle. This is a circle. Okay?
Okay.
A person here, you're gonna glide down. You wanna know the velocity here. Okay? Let's call this theta, and we're gonna count it this way, okay?
Okay.
Okay, let's get to a point. Okay. This at any circle, the tangent, which is the way this guy is gonna move, is perpendicular to the radius, linking there, right? It's called we call this theta. Okay, this is the direction this person moves, and this is mg, right? Mg is split it into this is f parallel and f perpendicular. This is f. This is mg, right?
Yeah.
If perpendicular is balanced out with this curve, you press it down, the curve presses back.
Yeah.
It's nothing, right? So all you have is f parallel, right? And this is mg. What?
Huh?
This is mg times what?
Oh, that's mg outside. I mean, cosine.
Yeah, cosine theta. Okay. So a equals to the acceleration of this thing. A equals to g cosine theta. Yeah.
Yeah.
Okay. A equals to dv dt. Let's see. A equals to. Let's see how we do this. You want to know the velocity, right?
Yeah.
A equals to dv dt, right? So dv equals to a dt, right?
Yeah.
So you want to take an integral of this v as it goes along, and then go from 0 to pi over 2.
Okay.
Yeah. You want to go do this from theta equals to 0 to pi over 2, right? This is what you want to find out, the velocity here.
Yeah.
Okay, now. A, we know is what? Where's A? Oh, here, yeah. A is g cosine theta dt. Right?
Yeah.
And theta dt. Let's see how this is done. dt. We want to change that into ds. We don't like dt's, right? We like ds. So, oh, wait a minute. Let's not do this that fast. This dv equals to g cosine theta dt, right?
Yeah.
Right? And actually, we don't want to do that. Actually, this is, I'm doing this the wrong way. Okay, let's go back. dv dt equals to g cosine theta, right?
Yeah.
Yeah. We want to integrate this against theta, right? And that's distance. Distance r d theta.
Okay.
Yeah. Now we're gonna do this. dv. Okay. Let's write it clean. dv equals to g cosine theta dt. Right.
Yeah.
Now let's move this around. G cosine theta d theta, right?
Yeah.
Right. This we can integrate. Take an integral over this. Okay. Now, obviously this is no good because this is not what we have here, right? So you have to divide d theta and multiply a dt.
Okay.
Right? And by the way, this is the velocity, right?
Yeah.
So you multiply on r, this becomes velocity. R d theta becomes the distance that this ball is crossing, or whatever a person is crossing this distance, right? It's r multiplied by theta. That's the length of this arc, we define angle that way.
Mm-hmm.
Yeah. So this equals to, I'm going to write it a little easier. Okay, g cosine theta d theta and my times r, right?
Yeah.
And then 1 over r d theta dt. Right. This is actually v. Right. So we change that into a v, g cosine theta d theta. R, we put r here, divided by v, right?
Yeah.
Multiply v over v dv. You know, we're solving this this problem. Put v on one side and theta on the other. We don't like t, right? We get the t. There's a velocity that connects t and the distance.
Yeah.
Theta is a factor about distance. So we change that into a distance. Then we introduce a v. Right? That v doesn't matter because this side is v. We just put it on this side.
Okay.
Okay. That equals to g r cosine theta d theta. Okay.
Yeah.
Okay. Now we take an integral from 0 to v. Right. Right. This is 0 to pi over 2. Right.
Yeah.
That's the velocity here is 0. We want to know the velocity here. This, in the meantime, the theta goes from 0 to 2 pi over 2. Yeah?
Yeah.
Okay, now. This, what's this?
Oh, that's v squared divided by 2.
V squared divided by 2, right?
Yeah.
Now 0, 0, 0, right? This is all in. This, I'm going to take the gr out. What's this? Cosine theta.
Oh.
Is the
Cosine pi over 2 is 1. Wait, 0.
no. What is this? Cosine theta. You take an integral, becomes 1.
Minus sign.
Yeah, minus sign. Okay, this is from 0 to pi over 2. Okay,
Yeah.
and pi over 2 is 1. 0 is 0.
Mm-hmm.
Right. So this equals to. Okay. Something is wrong about it. That minus sign is going to be a problem. Minus gr, right?
Yeah.
Okay. The minus sign is a mistake because let's see. dv is dt, right? dt going down. Then we do d theta cosine. No. This is plus sine theta. Okay, g equals to cosine theta, right? Sine theta take a derivative is cosine theta, right? Right? Sine theta take a derivative is cosine theta, right?
Yeah.
So cosine theta take an integral is sine,
Oh.
right? You're taking an integral, not taking a derivative. The other way around, right?
Yeah.
No, so we don't have this minus sign problem. Okay. Okay, now we have v equals to 2gr, right?
Yeah.
Okay. This is a little bit complicated, this process, right? So they don't teach you this way in whatever, high school, college, what you name it. Okay? The way they teach you is this ball here has a potential energy of mgr, right?
Yeah.
This is gonna, the ball gonna lose all of it here, right?
Yeah.
Here the ball will have no potential energy, but with all dynamic energy, right? This you can get v equal to 2gr square root. Okay.
Yeah.
This is, you ask why we do this, all of the work stuff, right? It simplifies things a little bit. But if you just look at the F equals to ma, right, you can do it.
Mm-hmm.
A little bit convoluted, but you can do it. That makes sense? It does or does not. When it goes down, right? When it goes down, at any given moment, you know the force on it.
Yeah.
Or you know the acceleration on it, which is this, right? Because the angle changes. When you put the angle in, this angle, you need to, oh yeah, let's just forget about this. This is two. When you put this, right? Because you need to take an integral of this, right? Theta and t, you can't do it.
Yeah.
So you need to get it into some kind of a distance thing, right? That's velocity. Velocity links t and the distance, right? So you do this. This you introduce the velocity, but that's okay. This is velocity on this side. You just multiply it over, then you can do it. Yeah. In other words, you have a this is your sort of equation. Your actually this the v dot equals to g cosine theta. That's your differential equation, so to speak.
Yeah.
You need to solve this differential equation. You can solve it, and then when you solve it from 0 to pi over 2, whatever, it'll be equal to this. But you can also do the do this energy or work scheme, this potential energy all converted to kinetic energy, all converted to moving.
Yeah.
Yeah, and then you come up with the same result anyway. This is easier, obviously. I don't think at least high school they don't even show you this. Okay. See you next time.